Farnsworth is the inventor of television. Even if you have a good idea, even if you have the original patent, you are highly disadvantaged because there's powers that are much more wealthy, much more lawyered than you that can basically run you into the ground. The energy would build up, and it would build up this little field in the middle, and that field would cause a little, a little glow or a little star to appear in the center of the bulb. He read a paper by Poisser. It was a mathematician that published different papers, and I think he was on a train reading a paper from Poisser, and this mathematical paper was basically a way that you could have stable waves that would form inside of stable waves. So essentially you would have a spring that was pushing another spring, that was pushing another spring, that was pushing another spring. So by having a field within a field within a field, each field would be denser and more intense than the previous one. And he applied that to what was now fusion, inertial electrostatic nuclear fusion. So the two teams that we have is the magnetic fusion, which is the giant donut, compress all the stuff with the magnetic field, and Farnsworth, which was going the opposite route, which was electrostatic. And the goal was that instead of the particles being smashed manually with a high DC current, they would basically be left to flutter or to oscillate in and out. And what would happen is if they applied a signal at the right point, it causes the bubble to get tighter and tighter. And because of this and a couple mathematical little constructs, if the system oscillates hard enough and strong enough, it gets to the point where you get individual fusion. George Bain killed the power immediately, but the fuser did not shut down. It actually continued operating as an increasingly bright light emanated from the pit. After this spontaneous operation had continued for at least 30 seconds, perhaps a minute, a, quote, pop and a hiss indicated that the stainless steel reactor vessel had been breached, releasing the vacuum, at which point the reaction finally ceased and the fuser cooled down. They had actually achieved positive, self-sustained nuclear fusion in a stainless steel vacuum tube. And essentially, when the system became self-sustaining, it produces a high voltage DC as its output. So the energy that comes out is constantly trying to push in one direction, which is a direct potential relative to the core.
It's weird science and freaking magic.
I just told the world how to build a free energy machine, is what I told them.
Yeah, what are we interested in this week?
Yes, I am interested in talking about who Philo T. Farnesworth is. I saw you had some interesting posts about that, and I thought, man, people really need to know about that. So let's do that.
Okay, so abridged version of Philo Farnsworth. So for the people that don't know, Farnsworth is the inventor of television. He is the person that holds the original patent for what was the cathode ray television that, well, was used until very recently, which is now LCDs and other garbage. But pre-digital, he did the first mass manufactured proper TV patent in the US.
So tube TVs.
Yeah. Farnsworth grew up around the same era as Tesla. I believe he was a little bit younger, so he came in, let's say 10 or 20 years later, but it was still in this field where electrical engineering was completely brand new. They were discovering, all they had was, wire, battery, maybe a meter. There was no test equipment. There was no anything. There was brass, copper, wood, iron, and everything they had to do was based on that.
Gotcha.
So Farnsworth, poor farm boy, I think he grew up in Iowa or something like that. He was always interested in electronics, and I believe it was radio at the time because there was people all over building, a little ham radio receiver, a crystal radio, and stuff like that, which was, groundbreaking at the time. It'd be like someone messing with like 3D printing 10 or 20 years ago when it was still completely new.
Right.
And somewhere during his thoughts in farm fields and experimentation, he had this idea. combined all these things together for this idea for television. And what it was is he saw people plowing the fields, and what they did is they went back and forth in this grid pattern across one
Interesting.
layer, then to the next layer, then to the next layer. So this grid pattern he noticed, and that led him to essentially come up with the idea for television, because what they could do with a TV is instead of trying to render a full picture, they would break it down into little tiny chunks, and each of those chunks would represent a scan line. So instead of trying to render a picture, take a picture and post it at somebody, they would break it down into little pieces, scan line by line, and use that to reproduce the original signal. There was actually
Wow.
a few different ways for that, but he wrote this. He wrote this on a little note and gave it to a friend or something like that. And then some years later, he actually filed for the patent. He had a small laboratory, kind of like Tesla's early days. The main issue is they were trying to figure out how to make a sensitive photocell, a sensitive and fast light receiver that could take
Okay.
the incoming light and turn it to electrical signals, because that didn't exist yet. It's like, there was a little photocells, but they were really slow. They were really inefficient. There was this whole thing of blowing glass tubes and, but
Are we talking about photocells in TVs, or is this still photography?
this is for television. It was the idea of how to digitize a signal. So this was
Okay, so
like,
so
it,
this
it
needs to
was,
light up and then darken and then light up again for the next picture. So you're looking for something very advanced.
it was a photocell, but the photocells that they had at the time, those little CDS, cadmium sulfide, there's these little ones you'll see on, light sensors and things, and they work. They're pretty sensitive for light, but they're not fast. They're really, really slow.
Okay.
So they had those at the time, and of course they were really, really slow. So what would happen is, well, if you're going to use that kind of sensor, it's going to take you 2 minutes to render an individual frame. So it's
Hmm.
like they had no technology to do that faster. So a lot of Farnsworth's laboratory early experiments were basically how to speed that up, and that got him into vacuum tubes with special coatings and other things. So uh, essentially he got to the point where he was able to create an image. What did they call it? It wasn't a digitizer. It was an image. I cannot remember the name, but it was the method to actually turn the physical image into a signal that could be amplified and delivered at range to another receiver.
Okay.
So around this time, I'm really, really paraphrasing here because it's been a while since I've read the read the
Totally fine.
biographies and whatever. But what happened from there is he finally got to a point where he was uh, able to patent and begin to start producing these products. But what was happening is at the same time there was other competitors. You'll know when Edison, invented the light bulb, there was another guy in Europe that was doing the exact same thing at the exact same time. And it turns
Right.
out, well, they both pretty much made the light bulb at the same time. They were on the same breakthrough.
Right.
Well,
Morphogenic field, in my opinion.
or whatever it is. Yeah. Farnsworth was not alone in his quest for digital, for television, because there was a whole bunch of people that wanted to send pictures over a distance. Uh, one of these, there was a British version. Instead of using a vacuum tube way of transcribing, what they ended up using was a giant light. It was like a wheel that would spin really, really fast, and it would have little dots, little openings. So when the wheel spun at a certain rate, they could do that scan line thing with a giant fast moving disc. And it
Wow.
was it was a completely different method, and it was kind of crazy and didn't scale very well. But that was, one of the things that was happening while Farnsworth was doing his version.
Huh.
But
Interesting.
what ha what happened around that time, I believe it was World War One-ish, is the big companies started to get involved, and Farnsworth basically ended up going against RCA, or what became RCA. So it was one of those David and Goliath stories where Farnsworth basically had the prototype for a television and was trying to get the patent recognition for that, and was going back and forth with the Supreme Court and the different courts for years, basically saying it was as if somebody had a patent for a cell phone and they were going against Apple to say,
Mm.
well, who has the original patent for the cell phone and who's going to get the royalties and the rights and things like that. So Farnsworth was basically, this one guy fighting Apple for the patent for the original cell phone. So
Right.
uh, eventually what it turned into was this note that he had written to a friend years ago when he documented this idea of using scan line, digitized image transferred over a distance. It was like a notebook, a note card type thing. That turned out to be the piece of evidence that got used, sent to the courts to say that yes, Farnsworth did have the original idea, the original inception of this patent, and so they
Interesting.
granted it to him. But as we know with large corporations, that's not the end of it. The next problem, let's say Farnsworth wasted 5 or 10 years of his life fighting for this patent stuff to try to get things out. Well, what happened was once he got the patent, these other companies started coming up with little agreements where they would not produce televisions for him or
Mm,
equipment or anything that was related to his patent. So they tried to lock him out from a supply side issue. And
wow.
it was a huge battle. He did eventually get, as we know, he did get enough of a critical mass. He got his own factories running that were making televisions, making recording equipment and things like that. And that did finally, build up a platform. But the the first half of Farnsworth's life is basically him fighting for the right to his own work. And if
Interesting.
you want anything that's an argument for against getting a patent and the risks that go along with it, Farnsworth's documentary or biography is a perfect example of that. Is that
Mm,
even if you have a good idea, even if you have the original patent, uh, you are highly disadvantaged because there's powers that are much more wealthy, much more lawyered than you that can basically run you into the ground. And
right.
they almost got him, back in the 1920s with that. And
Wow.
that system's so much worse now. So today, if you try to patent for something uh, against that type of power, you probably wouldn't stand a chance.
Wow. That's tough.
But the point is, why patent? What's the advantage to doing this? You're putting your name or your signature on something. If
Hmm.
you if you really want to change the world, it's not needed. We've seen the invention of Linus Torvalds, the guy who made Linux.
Hmm.
Basically, he didn't patent anything, he didn't trademark anything. He took a year of his life off and worked his ass off and programmed what was basically an emulator equivalent to IBM's Unix, and he called it Linux with his name and his information, and he just gave it away for free.
Mm,
And he's not a billionaire like Bill Gates is today, but his equipment is in more computers today than Bill Gates, and he will have a much longer standing legacy than Bill Gates will as a founder for an entire technology.
right.
He doesn't have a patent, he doesn't have anything. He lives off donations, but he still makes a decent living. He changed the world. It's all
Yep.
these good things. You don't need to grasp so hard to get credit for that.
Right.
And
And
besides,
that's
there's
what it's about is,
yeah,
is making the world a better place.
yeah. Well, the joke with this whole the free energy over unity, things like that, is uh you want to make a world where scarcity doesn't exist. Let's say you want to have a world where there's no limits, everything is completely easy, accessible, everybody's in a an energy paradise. And the
Hmm.
joke is, well, so you want to be a millionaire in a world where money has no meaning.
Mm, pointless.
It's what's the point of selling out if you're going to change the world?
Right.
So
Yep.
anyway, that's the first half. Farnsworth's biography is basically him, David versus Goliath thing, the major powers, and he finally got television. Uh, he got a foundation. He made all this difference. Happened later on? It was probably by the 40s and 50s, I believe. Is Farnsworth's history was highly with cathode ray tubes, vacuum tubes, evacuated tubes, because that was how you made the image intensifiers. That was how you made the actual televisions, the cathode TVs.
Okay.
So everything he also did, it was a photomultiplier, which was a method of amplifying very tiny light signals into larger signals.
Okay.
It's where you could take one photon and you can turn that one photon into a signal that's big enough that you can pick it up with a normal receiver. And that's,
And you would want to do this for broadcast purposes.
for very sensitive light receivers, there's all kinds of things. You would want a really fast, sensitive receiver that could pick up individual photons.
Okay.
maybe fiber optics, things like that. Yeah, all kinds of uses.
Hmm.
Especially TV, because you would have your recording equipment has to have a good contrast. You want to be able to pick up the lights and the darks and have a really good range, stuff like that. So basically, Farnsworth's history was significantly with vacuum tubes and this type of technology, making amplifying images, uh, amplifying signals and stuff like that. So what happened was he got to a point with where some of this equipment, it was the photomultiplier was one of them, where you put the thing in you send either a small signal or you send a photon, and when it strikes an object, it amplifies back and forth, bigger and bigger, until it sort of cascades into this resonant, sort of vibrates like a spring. It's
Okay.
this very strong amplifier, and supposedly what happened was that when he operated this multi-pactor at a high enough energy level, that the energy would build up and it would build up this little field in the middle, and that field would cause a little a little glow or a little star to appear in the center of the bulb. And
Okay.
the ball was basically an ionized it was an ionized plasma in the center of the evacuated bulb. It was just kind of like a glowing neon, whatever. But
Hmm.
he saw that this was forming in free space, and this was completely novel. Nobody had done this before.
Huh. Okay. So
So,
this was before fluorescent light bulbs.
concurrent with them, fluorescent bulbs hadn't taken off, but it
Uh-huh.
was it was in his field, which was vacuum tubes, amplification, RF,
So
that type
fluorescent,
of tech.
forgive me for being a dumb dummy now. Fluorescent bulbs have gas inside of them. What Farnsworth was working with is completely empty.
Completely empty or
Or,
inert gases, things that it's trying not to react with anything.
and he's
But it
seeing plasma inside of it.
yes,
Okay.
and but it was sort of what drew him in a certain path. And then what happened was he had this multi-pactor, and it would basically make a little star in a jar, like what you would see in the Farnsworth fusers, where
Okay.
there's the purple glow or the blue glow and the thing sitting in there. That was
Uh-huh.
pretty much where it was at for a while. And at a certain point, he read a paper by, I forget his name, but it was Poisser. It was a mathematician that published different papers. And I think he was on a train reading a paper from Poisser, and this mathematical paper was basically a way that you could have stable waves that would form inside of stable waves. So essentially, you would have a spring that was pushing another spring that was pushing another spring that was pushing another spring. So
Hmm.
by having a field within a field within a field, each field would be denser and more intense than the previous one.
Huh.
So he saw this formula, this equation, whatever, and realized that that would get him the critical mass that was needed for nuclear fusion. And say, well,
Okay.
this energy density at this, you do the back of envelope math, and it turns out you can get to fusion energy levels, at the center.
Okay.
So that was his breakthrough. That's what set him off. So
Wow.
he took his multi-pactor and the technology with vacuum tubes and whatnot, and he applied that to what was now fusion. And this was where what we know as the Farnsworth fusers started coming off.
Okay.
So he did years of experiments
I'm
with
trying
this at
to
this point.
excuse me, I'm trying to contextualize this. So this is, I'm assuming, after, the nuclear era has come underway and people know about splitting atoms, but they're not too familiar with ways to fuse them. Or I suppose it sounds like some.
1940, we'll say 1950s or so, which was when we knew we could make atomic bombs. We knew we could smash things apart and have nuclear reactions, but
Okay.
they were on the edge of trying to do that in other ways. So one of
Okay.
them was, the hydrogen bomb, where, oh, we have a fission bomb that sets off a fusion bomb that, these
Okay.
different breakthroughs based on that. And I believe they were able to induce fusion on the atomic level, but it wasn't anything that was considered a viable technology. It was something that you had to do within particle accelerators and, crazy conditions, that kind of thing. Maybe lasers. I forget the exact details. I'm not the best source, and it's been a while.
Oh, that's fine. I'm
So,
learning just, I haven't studied fusion whatsoever, so this is all
well,
new to me. So,
we'll say it's the 50s, so it's that era where nuclear is the big craze, fission and
okay.
fusion. This was when the USSR started building the tokamak reactors. These
Okay.
were these gigantic magnetic. They look like giant donuts, And the
Okay.
idea was that, well, you take the deuterium and you compress it enough with a giant magnetic field until it turns into that little sliver, and that hits the energy densities needed to fuse it into helium, and there's your fusion
Oh,
reactor. So this
okay.
was the same era that was taking place, was the giant magnetic fusion reactors. Farnsworth was going the opposite directions. He was working with electrostatic, you know, star in a jar reactors.
Okay. So this is inside of glass, and obviously it's not causing an explosion massive enough to bust out of the glass.
They some with the right gas mixtures and compression and things like that, they were able to get fusion to occur, but it was in
Uh-huh.
tiny individual events. So what was
Huh.
happening is Farnsworth started where he knew there was a math behind it, he knew there was something going on, and they were experimenting to try to get it to work.
This is the problem right here. This thing needs to be thrown in the garbage, is what the problem is. I
As
do
Eric would
have,
call it, the China box.
yeah, I do have a Zoom, as in a Zoom H6, which is a lot nicer. So here's what we could do. If you're free tomorrow, around the same time, I'm free as well. I'll see if I can, get all of that working the way that this thing's supposed to be working, and then we could pick up from there. Does that sound good?
Let's finish this one thought. We can pick up tomorrow, but I think I can, since I guess it's going to be recording on my end anyway, the audio should be okay. So uh so we were talking about Farnsworth. Farnsworth's history, fighting RCA for the rights to his own patent, about a, spending about a third of his life inventing television, about a third of his life fighting for the patent for it, and the last third of his life was with inertial electrostatic nuclear fusion. So, to set the stage where Farnsworth is in his life and where we are on the world stage, this is sort of the 1950s, I believe. And this is when, the nuclear bomb had been set off. This is where fission and fusion are basically the big thing right now in terms of energy research breakthroughs. Uh, of course, it's amplified even more because there's the US versus the Soviets trying to lobby for the next big thing, the next giant breakthrough. Around this time frame, we basically have two teams that are going on that are hunting for the nuclear route. We have the physicist route, which is the magnetic fusion, which is the tokamak reactors, which is basically using giant magnetic fields to try to push everything into the small bubble to get fusion that sustains the system. And you'll know this tokamak style is what we're still working for today. So and that in the 2020s, we're following up on the same tech from the 1950s, and it was one of those jokes where it's always just 20 or 30 more years down the road, and then they'll have some viable tech.
Mm.
But just to say, so that started in the 1950s, and today we could we could pretty confidently say there's been over $1 trillion of research in that direction, and it's still about as far off now as it was back then. So sidebar aside. So the two teams that we have is the magnetic fusion, which is the giant donut, compress all the stuff with a magnetic field, and Farnsworth, which was going the opposite route, which was electrostatic. Because Farnsworth history was working with vacuum tubes, evacuated tubes, cathode ray tubes, everything was evacuated bulbs and similar things. His approach instead was to use strong electrostatic fields. And the goal was that instead of the particles being smashed manually with a high DC current, they would basically be left to flutter or to oscillate in and out. And what would happen is if they applied a signal at the right point, it causes the bubble to get tighter and tighter. And because of this and a couple mathematical little constructs, if the system oscillates hard enough and strong enough, it gets to the point where you get individual fusion elements at the dead center of the unit. So uh, Farnsworth had been working on this. They were able to get individual fusion events, but of course not a self-sustaining system. It's one of those ones where they could detect neutrons and they could detect other things, but they were experimenting with different gases, different pressure levels, different potential levels, different current levels. There's so many variables to working with these tubes that, it was trying to nail down what are the critical factors and things required. So the quote that comes from his biography I'm going to read now, which was Fred Hock described an occasion when he, George Bain, and another engineer named Jack Fisher were preparing the fuser for a metered run that would be conducted the next day. There was no instrumentation on the fuser during the setup. As was often the practice, the workers were putting the fuser through its paces, making sure its systems were all functioning, when, according to Fred Hawk, quote, the fuser in the pit just lit up and went crazy. George Bain killed the power immediately, but the fuser did not shut down. It actually continued operating as an increasingly bright light emanated from the pit. After this spontaneous operation had continued for at least 30 seconds, perhaps a minute, a, quote, pop and a hiss indicated that the stainless steel reactor vessel had been breached, releasing the vacuum, at which point the reaction finally ceased and the fuser cooled down. This is from the Boy Who Invented Television biography that I'm sure you can find on Amazon. So the story is that they had actually achieved positive self-sustained nuclear fusion in a stainless steel vacuum tube, basically. And the system continued to operate on its own volition until it just melted down and, broke the cycle. So that is essentially where all the official stuff ends. I believe this incident is considered more of a rumor than anything. It hasn't been, validated on any level because obviously nobody's replicated it, so we can still call it essentially a miracle or a story. So in terms of the modern physics, this is either considered a urban legend or something similar, but at any rate, it hasn't been reproduced, so they kind of gave up on it. So this point in Farnsworth, he was getting pretty old. He didn't have a lot of energy left in him, not too many years left in the tank. And basically, I'm taking up from Dollard's explanation from here on, which was they continued to make different types of bulbs and experiment with different potentials, and they did get some factors that would create consistent, sustained fusion in the bulbs. But the problem was they would only last, quote, about 5 minutes, 5 or 10 minutes, before the heat would inevitably cause something to melt down, releasing the vacuum and stopping the test. So according to Eric, the follow-up was after this experiment, they had continued refining the process and getting some better results, but transcribing or releasing the heat was always a problem. And at a certain point, Farnsworth basically, died, and his team or whatever circumstances, there wasn't an infrastructure that he had built that was able to pick up and continue his work once he had gone. So basically at the university where he was operating in the laboratory he had, once Farnsworth died, it was everything was sort of scattered. His notes and things may have gone to his family. The equipment might have gone to other professors or other universities. All of this stuff just sort of scattered to the wind, and Farnsworth was basically lost. His knowledge was basically lost. So the only people that I've seen that really mentioned or followed up on this would be Eric Dollard from his escapades with Philo Farnsworth's son, which not a very enterprising individual, but they both hung out for a while, and Eric did get some behind the scenes and more details of what was actually going on around that time and afterwards, and where they had left off at. And Eric had also, of course, seen some of the original bulbs that had the sustained nuclear fusion that had taken place in them and was experimented, and better yet, he knew how the stuff was operating, so he could have the high level conversations of what the fuck was actually going on here. Wow. But the story basically ends at that point because Farnsworth died. Dollar didn't have the resources to pick it up. His son, universities, a lot of the information and knowledge was basically lost at that point. But the point was that it had enough potential and enough, we'll say, threads of success that anybody with the proper knowledge and skill set could probably build one of these things and get it to work. It might be a 10 or 20-year project, but we know it's already worked once. So there's a definite destination in mind. We weren't like Farnsworth, where you're literally just stabbing in the dark trying to hope for the best conditions. We do actually have some guidelines as to what's going to work and what isn't. So to bring you to today, as you know on the internet, there are a bunch of Farnsworth fusers where you'll see these grids have been grids that have the little star in the jar that lights up. And a lot of these are actually nuclear fusion devices. They do produce fusion events, as can be detected by neutron counters.
Wow.
But the problem is these systems generally are very low power. Obviously the fusion that it generates are individual, tiny, minuscule events. Let's say 0.1% of the power that's actually going into it. So they obviously need refinement. There's a lot of different factors that can be improved on these. The major factor that I see is in the fusers that are online, generally they operate on an arbitrary high frequency DC potential. So essentially it's basically plug a high voltage source into it. The potential causes, this oscillating effect and it creates a star in the jar, but they're not tuning it in any way. They're just firing random RF at it, and eventually something does smash together and happen. I think the main bottleneck that they're probably facing is that they need an RF engineer or somebody that can help tune the system, because what happens is in a proper system, what would happen is the energy that gets delivered into it is actually reciprocated. It oscillates within the chamber, and if you have a frequency just right, it becomes something like a tuned circuit. So instead of needing to pump a kilowatt into it, you might only need to pump 50 watts into it to get the same energy densities. This is the same where you've seen people build Tesla coils or things called Tesla coils. Somebody might pump 10 kilowatts into it, and they'll get this little tiny arc discharge, little faint garbage thing. And then you'll see someone else that's working with a 40-watt transmitter getting, lightning bolts. So they're both technically the same system, but one is tuned much better. One understands the operating principles a lot better and is able to push a lot more out of such a small system. Actually,
Okay.
there's a joke, is the first lecture that I gave on Tesla coils, I had compared, what was it? Electro Boom was working on a Tesla coil at the same time that I was. And he was reporting, I had a screenshot where he made this long, thin, quote, Tesla coil. It had thousands of turns, and he had it next to the bench meter, so you could see he was putting 20 watts into it. And he had one of these little compact fluorescent bulbs, and he was just barely lighting the fluorescent bulb from like 6 inches away. That same day, I was following up on Eric's work, building my own coil, and all it was just one single coil, and I was lighting the full fluorescent tube, the 2-foot tube, from about 2 and 3 feet away, with what turned out to be about 1/3 of a watt. So I
Wow.
was almost 2 orders of magnitude less than what he was doing, and getting orders of magnitude better results out of it. It's because I was going on the principles Eric was following, which was essentially tuning efficiency. There was maximizing the efficiency of it rather than just banging as much power in and hoping you get a result. To
Right.
loop back into the Farnsworth side, I think there's a similar issue or similar weakness with a lot of the replications today. And it would actually be nice to work with a Farnsworth replicator, because we might be able to put things to a certain power level and tune things to a certain extent and modify the design so it matches what Farnsworth was doing,
Hmm.
and they might actually get some sustained, permanent effects out of this. It could be right around the corner.
Interesting. Just 20 or 30 years away. Hopefully not with this.
The fact that you could outdo them with $1,000 in parts is just kind of amazing.
It's incredible. So when you say you can outdo them with $1,000 in parts, is that in reference to the Tesla coil, or are you talking about fusion here?
Yes. I was talking about fusion, but that actually would apply to the Tesla stuff as well.
Wow.
The fusion is, the tokamak, the giant physicist fusion reactors that have literally spent more than $1 trillion over the last 50 years, and they're almost where they are back then. There's still massive problems. They're not harnessing any energy out of it. They might have self-sustained fusion that might even be power. It might even be putting out a little more power than they put in, but it's putting it out in thermal energy that can't be recovered with 100% efficiency. So they're
Mm.
still not at COP1. They're still putting more in than they could possibly get out.
With IEC fusion, do you get power out as heat or something else?
Great question. So in Farnsworth's setup, what he was referring to is in his original lab and also corroborating with Eric is the system was basically fed with DC that was in an oscillating circuit. And essentially when the system became self-sustaining, it produces a high voltage DC as its output. So
Wow.
imagine 5,000 volts at 15 amps or something, I don't know what the number, an arbitrary number, but it would be a high voltage at a significant amperage. As a byproduct, it would produce a lot of heat, which in the Farnsworth case is a problem because it eventually melts down your reaction vessel. But even if that was an unsolvable problem, like, you could potentially put, run coolant or something through the grids or through the chamber, try to keep it managed that way. But even if that wasn't a viable system, well, let's say you could only run it 25% duty. So have four fusers. You run the first one. When it gets too hot, run the second one. When it gets too hot, run the third one. There you go. 100% on time nuclear fusion. And thermal is just a problem.
And my understanding is when you're drawing this power, it works on resonance, right? So when I strum the E string on my guitar and then I hold the E string, I can hear the high E string ringing in resonance. And that high E string ringing is not taking anything away from the low E string. It's just taking advantage of the sound wave that's traveling through the air and resonating. So if you have a bunch of arrays of something gathering this power from IEC fusion, you're not actually creating a load on the original system, right?
Well, the energy that's required to get the fusion event, basically the electrostatic power that's required, what that electrostatic potential is doing is it's pulling or pushing, depending on perspective. It's pushing everything in with a certain amount, and that requires, that energy in that direction. When it finally hits the middle and the fusion event happens, that creates energy in that direction. So the energy that's put in, you get a bigger bang out of it. So it's maybe pulling a trigger on a gun might be a bad example, or lighting the fuse to a bomb or something like that. The energy that goes in is not the same as the energy that comes out. And
Right.
the reason why
Okay.
it's DC is because the potential that goes in is predominant, is in the end, it's an oscillating DC, but it's DC. So the energy that comes out is constantly trying to push in one direction, which is a direct potential relative to the core.
Interesting.
My understanding,
Wow.
anyway.
Cool. Well, I can't wait to talk more about this. And I also can't wait to get my audio fixed. So,
This
do
will
you
be
want
our
to call
first.
it there for today?
Yeah, this is a good first experiment, as everything that we do, both with media production and on the bench and all that. These are all experiments. So
All right.
I think this was fun. We could do another one of these tomorrow.
That'd be
Could
great.
be